HIFI-ELEMENTS, introduced by Jens Ewald, who is the project coordinator of HIFI-ELEMENTS and senior project manager at FEV Europe in Aachen, Germany. Dr. Jens Ewald graduated in mechanical engineering and energy technology from Aachen University in 1999. It's still not 1984, but we're getting closer. And gained a PhD at Aachen University in 2006 on simulation and modeling. He held several technical positions in simulation at FEV, and since 2016 has held the position of Senior Project Manager for ICE development and vehicle calibration. Currently, Jens is coordinator for both HIFI-ELEMENTS and the Sublime Battery Research Project. What a cool name. Jens holds several publications on combustion theory, crank angle, ICE fluid simulation, and battery electric vehicle simulation. Jens, are you there?
Yes. Okay.
Perfect.
Yeah, Andy, I think we have quite a lot of things in common. You know, you were talking about IC crank angle resolutions and so on. I think this is still quite.
Those were the days, hey Jens.
Yeah. Okay. I will present the HIFI-ELEMENTS project, and HIFI-ELEMENTS is an acronym for High Fidelity Electric Modeling and Testing. And to say, okay, I was the coordinator of HIFI-ELEMENTS is not completely correct, because I would like to also give acknowledgements to Thorsten Schnorbuss, who is staying behind in coordinating this project, but he was the one, who wrote the proposal and finally fought with our consortium members to get the grant, and now I am technically coordinating this. So what is HIFI-ELEMENTS in short words? It's a research project in the same call as OBELICS, of course, as you can imagine, and we have 16 partners all over Europe. So they are from engineering services providers as FEV are, for example, but also we have tier 1 suppliers here and not academia, research institutes, both from academia and commercial institutes, as well as the OEMs that you see here. In particular, it's Iveco, it's Ford, and it's Fiat Tofaş from Turkey. The work scope in HIFI-ELEMENTS is basically centered around improving the development of battery electric vehicle development. And it's started our project in the same time as OBELICS, so October 2017, and also here we expect to run until the end of the year due to Corona. Our work scope is the development of the effort-saving automation methods for calibration and testing, and also by means of this increase of the test coverage. And the second pillar is circulated around standardization. So standardization was already some topic in the presentation of Horst, and here we say we want to standardize the simulation architecture for BEVs, as well as their components and their signal interfaces. And once after having done that, of course, we also want to implement this and develop and have a tool chain for the simulation data management. And that helps you also to introduce co-simulation. And what that will mean, I will tell you in a second. So all of that is being validated, not against, let's say, 11 use cases, but we have 4 industrial relevant use cases that really prove currently it's still ongoing. And I'm happy with you to show our results. I mean, we are 95% finished now on that, how far and what kind of results we can gain with our developments. So I want to make it very simple in the very beginning, because there are lots of technical things that you will see during the run of the day. Where do we need, let's say, conventions when it comes to simulation and testing of battery electric vehicle components? Here, very simple, you have this vehicle that you see here, and I will just pick out 3 of these components: the battery, the inverter, and the e-machine next to, let's say, the mechanical transmission. And that needs to be simulated. And how do you do this? You want to do this, for example, for something that you call model in the loop, where you just do the simulation, but later on you want to also pick it out, one of these components for hardware in the loop, where the rest is being simulated of the whole vehicle. I will leave out, the thermal discipline that you have. I will leave out the controls that comes later. Yeah? So we know the physics of this. There are electrical currents, there are torques that have to be modeled. You do it in the way that you say these components that you have, the modeling components, they have to exchange signals. So And sometimes it's very easy to do it. Let's say for the mechanical system, you say, okay, the EMotor has to communicate the torque to the transmission and finally to the vehicle wheels, while those ones will feedback the speed of the rotor according to the speed of the vehicle and such. Also, the communication of the signals, it's not really that you have to plus and minus currents that you model. You say, okay, I have to model the signal, let's say, of the electrical current, which goes from the inverter, what it wants from the battery, and the battery finally tells then, based on that and the current state of charge, what's the voltage of the battery that it can deliver. But sometimes, okay, when you do modeling of components, it's difficult to say what should be the input and the outputs. For example, for the EMotor to the inverter, it could be both ways, So what model should really then give the signal, what's the inputs and the outputs? And that way you have to have conventions. When it comes to heterogeneous development teams, they have to agree on something. So this is really important. Next to this, we come to the topic of levels of fidelity. That means here you see, for example, the rotary current they're just being modeled in a DQ frame. So that means, well, okay, this is not really resolving the first harmonics. But if you want to resolve the higher harmonics of these rotary currents, when it comes, let's say, not from medium fidelity or from low fidelity models to high fidelity models of very high time resolution, you have to do this as well. And so you have to change this again and exchange different signals. In this case, it would be like the three-phase vectors of the rotary current. So this is one of the things you have to think of. What is the naming convention between these things? People have to agree on how to name these signals. And if it comes then also to the inclusion of, let's say, different development softwares and tools like FMI, which Horst already has mentioned, or MATLAB Simulink, or if you just hard code this in C or C++, it's always where you have to have conventions, what's data types and so on. So this is basically the objective where it comes from. And if you see this in a bigger picture, for example, from, let's say, the simulation or the development procedure, you start in different phases of the development of your battery electric vehicle. Let's say you start in the project concept phase in the very beginning, and you want to end up, let's say, with your vehicle investigations or with the test bench investigation. So initially, you start in having just very fundamental questions like, what is the best vehicle concept that you want to have? How many EMotors do you want to have? What is for the battery? What kind of capacity do you need just to fulfill all the requirements from the customer level? What kind of EMotor do you want to have? Do you want a permanent induction machine? Do you want an asynchronous motor on which wheels, front and the back? Maybe you want to have an EMotor on each of the wheels. So this is what you start to think of, and then you start to talk to the suppliers. And initially, you have just very rough approximations on how these models will behave. And once you have made the decision, you start to discuss in detailing phases with the suppliers. You will further then look at this, and also you will switch the focus from the system level to subsystem levels, where really the individual development teams start to optimize, let's say, the subsystems in more detail with the information of the suppliers. And also here, where you really work with low fidelity models, here you start with high fidelity models. You have very high time resolution, and you do the simulation and optimization, but it's not real-time capable. But when you go over, when introducing controls in the subsequent steps, you have to become real-time capable. So again, you have to switch your models. You have to go back to low fidelity models, but real-time capable. You have to introduce the controls. You have to make sure that they work in the model in the loop framework. They have to make sure that they work in the hardware in the loop framework. And each of these steps that you do, they create issues. So it's not really easy to do the transition all the time. You have different requirements, you have different development groups possibly, and they are looking on, let's say, different conventions, as I mentioned before. This is the basic, let's say, state-of-the-art development process. And with HIFI-ELEMENTS, we want to make it easier, because we say we introduce an encompassing interface in architectural standard for all of these design phases up to the point where test bench investigations are being done, and make sure that that you can seamlessly do the transition from the one phases to the other. Make sure that there is an interactive work of a collaboration between the development groups when they can, let's say, limit themselves, have the same standards. And also we introduce co-simulation, which means that it helps you to integrate heterogeneous simulation tools. So you don't have to limit yourself to whatever simulating FMI, FMU only, but you also could include, by means of co-simulation, commercial tools like Cooley, GE Power, Amazon, and so on. So this is basically what we want to do. And how do you do this? I mean, it's very clear that in the very beginning, when we thought of this, it's a very holistic approach. So you have to start with the collection of the requirements. And here again, we see, let's say, the classical model according to the V process. So also Horst showed a similar picture. It's not exactly the same, but it's very similar. And the idea what we had is we want to have this, let's say, in a very holistic way. Usually this process is being depicted in 2 dimensions. When you start with the customer value, you start the requirement definition, you start the implementation. At the end, when you have the realization, you go up and do all the test cases. When diving down this process, let's say you decompose your steps with the decomposition of your system into the subsystems. Well, we wanted to, let's say, have a front loading of the requirement definition, and we have adopted a procedure which stems from, let's say, from the method of model-based testing of software-based functions, because our observation was that different stakeholders each have different views on the system or parts of it at the same time. So in order to allow interdisciplinary front-loading of development activities by the different stakeholder groups, we introduce now another dimension in this development process. So next to the dimension of system abstraction, we allow also for an additional decomposition of the system into clearly arranged and manageable subsystem views. And that means we are able to look at the complete system in a so-called black box view, where we have the customer benefit in focus and derive requirements from there without needing to know how the system exactly works. Other views then can be described as so-called white box views, which resolve the technical function or also the internal structure. And requirements can then derive from these views in addition. This comprehensive requirement definition procedure, by this parallel work of different stakeholder groups, requires, of course, some other introduction of other means. Well, here we formulate and collect them in a formalized system description language with textual additions. In this case, it's called SysML. So by means of this, we reduce implementation risks during the system integration, and with the, of course, the corresponding reduction in efforts and costs. In future, this formalized description by SysML will allow us to generate corresponding test cases automatically, but this is coming out of future work. So what we have derived in the HIFI-ELEMENTS project is applied to 2 different BEV transporters. They have been derived from the Fiat Doblo and the Iveco Daily. So here we focus, of course, mainly on the electrical powertrain, and we have partitioned the system according to those components. So in this case, we did not look at the decomposition of the different physical domains like the mechanical, the electrical, or the thermal domain, which we would do usually if you have, let's say, a dedicated tool, for example, for the thermal domain, as for example, Cooley is. Here we said we partitioned according to the components, and we grouped also the components and their corresponding controls to one of these component models. And by means of co-simulation, we are able, let's say, then to perform something which is very important. For example, the thermal domain, which usually would comprise the whole vehicle with all the components, just is limited to the vehicle. And we are able, let's say, to continue the thermal domain, the cooling of the e-machine, of the inverter, and of the battery in their specific component models, and make sure that the inputs and outputs, then they are being transferred by our co-simulation tool XMod that you see here. So that allows us basically a flexible exchange of simulation models in between. So that helps you, of course, then to do some kind of optimization loops in the very beginning, where you think of, what are the right components that you want to use by a more or less, let's say, simplified plug and play approach. So this is, in very brief words, the HIFI-ELEMENTS project structure. You see here the work packages which are technically related. So the first three work packages here, they took care of this requirements and standardization, which I mentioned before. The component simulation models were another work package, and the tool chain, the model, the data, and the simulation management was the third work package. You will learn more from this in, let's say, the first presentation booth, which is called Proposal for a Simulation Standard and a Simulation Tool Chain. And all the four use cases, two of each will then be presented in, let's say, in the subsequent two presentations that we do from HIFI-ELEMENTS. So the first use cases, which were, let's say, circulated around e-machine and battery development, it's being called from model in the loop to hardware in the loop, because this is what they did. So you will learn more on that. The remaining two use cases, they were taking care of the topic of optimal operation strategies and the simulation for an optimal BEV concept. So what does that mean in detail? What will you learn? So the booth B, you will, first of all, we will explain to you ELEMA, which is our electric modeling architecture. This is an architectural standard proposal that we have developed, and we have published this, and you can use it for free for your own work. You can download this from our website. So it does not only comprise the two vehicle architectures of the two vehicles that I showed before, which are front and rear wheel driven BEVs. So we introduced more architectures of this kind, even to such fancy things where you have, EMotor for each of the wheels. So this is the one thing. The second part is we will explain to you the simulation tool chain and its data management. It's all circulated around the software Synec from eSpace, which basically drives our whole simulation approach. So it manages, the component models and makes sure that the integration of this by corresponding validation of the interfaces of the component models works, so that you know that what you're plugging together will at the end then lead to a final successful simulation. It performs the actual simulation just by triggering this. What it also helps you to automatically generate and run test cases. So when it comes to testing, we have a testing language which is called Tevit, which can generate many test cases at the same time, just for, let's say, functional testing. It also helps this tool chain to parameterize models. That means sometimes you will have seen this as a model calibration, but in this case it means that a model is being parameterized against a certain desired physical behavior that you know from the hardware system. So this is the first presentation part. The second one, as I said, it will cover from hill to hill. So for the EMotor in the loop, we will show to you that we are able to run an EMotor on a test bench in a transient way, as if it was in the simulated vehicle. And by means of our developments from HIFI, then we show that we are able to perform changes in the virtual and real components with minimized effort. So it's basically a plug and play then between different EMotors that we do. And here in this specific case, we show you the comparison from model in the loop to hardware in the loop, which of course then helps us to improve our development because we have much quicker turnover times. When it comes to battery in the loop testing, so Proofstone is here a battery prototype module, which was now allowed with our developments to be tested in early stages in a controlled environment with high repeatability. And both of these hardware in the loop test cases, they are coupled to, let's say, a realistic vehicle model already in the early stages of the development, which we had in behind because of the components models which were developed and which I mentioned before. So, and when it comes then to the last of the three technical presentations here, first of all, industrial electrification project is one of the things where the partners then exercised the high fidelity model exchange between stakeholders quite intensively to see whether our objectives that we had set ourselves really work. And they used the project toolchain for a quick and seamless interaction, used scalable models, so going from high fidelity models to low fidelity models. How does that work in practice? Of course, and they did real environment testing just to, let's say, calibrate models for the vehicle, for example, and doing real route mission profile optimization. So here comes controls into play, of course. So what could be, what kind of control strategies can you develop, let's say, for a vehicle in terms of road profiles and so on, to see how much energy we can save out of that if we have the possibility to test, let's say, our vehicle control strategies by means of this. The last part of that is the determination of the most efficient powertrain configuration by simulation front loading. So this is very, very similar to, let's say, the project concept phase I showed on the very first slides, just, you know, to switch through the different models and also implement, let's say, different temperature protection derating methodologies to come up, let's say, with the optimal configuration of the final model that we want to use. Okay. So when it comes, let's say, at the end to the topic of how much can we reduce our efforts by the developments of HIFI elements, because this is one of the main important objectives of this project. Here you can see what we think from today's point of view, how much we can optimize. So first of all, here it takes care, and we consider, let's say, the whole procedure from the simulation setup of the architecture, the generation of the component models, the adoption of the simulation models between the different fidelity levels, up to, let's say, the final test plan setup and execution. We have calculated the reduction efforts by all of our individual developments. So what we had postulated was this predefined architecture, which is called 150%. And what this means, then Marcus will tell a little bit more later on. We think that we can, let's say, here reduce quite drastically all our efforts here. And at the end, we believe if you sum this up somehow, just for all the efforts until you start and trigger the simulation, we can come up with, let's say, a reduction of overall 60 to 70% in the manual setups. And at the end, you can decide by yourself for which benefit you want to use these achievements. Either you use it for a quicker simulation turnover, or you invest it into increased test and simulation coverage. Basically, it's up to you. Well, coming to the three projects here, OBELICS, DEMOBASE, and HIFI-ELEMENTS, they are all members, as you may have learned already understood, of the same LCGV07 research cluster within EU Horizon 2020. And when they wrote their proposals, of course, they did it in some kind of a competitive manner, you know, and until the grants, the grant agreement came from the EU, we started to collaborate anyhow. And that's all I think also good. And you see there are lots of similar things between the projects. OBELICS and HIFI-ELEMENTS, for example, they're also very simulation centric, and of course they also share quite a lot of objectives. And these two projects, they exchanged very early already development results in the initial phases here. So you see here, for example, the exchange that we did in April 2018 in Paris. So the system model identity card was shown. The one that Horst showed in his presentation, we exchanged the architectural standard proposals for BEVs, as you already also saw from, if you compare Horst's slides with my slides, and we did lessons learned exchange on FMU and FMI. So, and then at the end, or almost at the end, early this year in Brussels, here you see the picture. It was just before the pandemic. Nowadays, it's very difficult to imagine that you see so many people staying closely together, but these were the times, and it's not that far away. We did then have a greater exchange also with DEMOBASE in terms of battery modeling, and again on the updates on standard proposals and simulation techniques in general. So here I'm coming almost now to the end of my presentations. What are the takeaways basically out of that? What I hope that you will learn from the whole day, not only from my presentation, but also from the presentations of DEMOBASE and OBELICS. So speaking for HIFI-ELEMENTS only, it's it's that we have proposed a BEV simulation architectural and functional model interface standard, and that is publicly available. So you can download this, access this from our website, HIFIELEMENTS.eu. It covers the main components of a BEV. So that means specifically e-machine, inverter, DC-DC converter, the battery, the vehicle dynamics, environments, and so on. It was developed, and I think because of the holistic approach in that short time, it was only possible by a systematic development approach using systems engineering-based methods. We support co-simulation, X-in-the-loop tests, as well as public standards as FMI and FMU, which also Horst mentioned. And with the several use cases that you will see later on, which I just briefly mentioned, we can show that we can drastically improve the workflow of simulation by means of front-loading and development activities by virtualization and an increased simulation and testing coverage. So this is it. Yes. I hope we'll have a great day today when hearing all of our presentations.
Jens, thank you very much.
You're welcome, Andy.
Very interesting. I've got a few questions. Sure. On a silly level, and then there's some detailed questions that I'll show in a moment. My silly question.
Mickey Mouse questions, always keep it simple and stupid.
What is the secret sauce of HIFI elements? Is it systems engineering?
I think it's, there are many secret sources. Systems engineering is one of it, maybe. So try to do it in a very systematic way, but it's also the willingness of all partners to work together and make results really, really public that other people outside of the consortium can use it. Let's say like the interface standard and the architecture and such things. Yeah.
So the tool
and of course
itself,
also at the end, the software, which will also be publicly commercially available.
Right. So he's saying that the systems engineering approach is one secret sauce. The way people behave and can use this is actually another system of systems, and the whole thing is a subsystem of your whole approach. So the secret sauce is system of systems thinking for people, disciplines, and the activities that you have.
Yes, and the collaboration of the different development teams, which should start, let's say, in parallel. And of course, this is like a zoo of fleas, and you have to, make sure that how can you really, manage this. And for this, of course, you have to introduce things like system engineering approaches, and here we use the system language, SysML. Just to manage it, yeah.
Okay, there's a couple of questions here on the chat. I forgot to mention questions in the chat, please. From Olivier Tabaste from MSC Software. He says, in respect of the standard model effort, did you have a change to review along the state-of-the-art stage MOSEC, the modeling and simulation information in a collaborative systems engineering context proposed by Airbus as a standard?
Okay, you are referring to the let's say to the aerospace industry. So we are here more in the automotive industry. This is let's say a slightly different discipline, but at the end, I think it's very clear that we should bring all these disciplines together. But of course, we come with different people with a different background, and so we have to manage those ones here. So we are more, let's say, influenced by work like ASAM standards, coming from the automotive industry, as I say.
I just read the question again. I suspect there's a typo, and you might have meant, did you have a chance to review the standard proposal?
This would be, let's say, the second aspect of the question, but thank you very much for reminding me. Of course, you have to see this has to be iterated somehow. So we have evaluated this now in a, let's say, smaller group. We have made it available to more research groups as the ones of OBELICS, and of course it should be iterated further. That's very clear. So the question is, do we have the chance? If there is an audience that is interested in this, yes, we definitely will have that.
Okay, so the answer is not yet, but you'd love to.
Yeah, well, the work, it's always somehow, once you have finished one step of the work, you will have an outlook, what's next, yeah?
Okay. Okay, I've got two more questions for you. I think we still have time, yes. From Willem. The multi-dimensional systems engineering in which you combine simulations in a black box, does that take any significant overhead for processing power? Is that a major load during the calculations, or is it relatively minor?
Well, the thing is, it was the collection of the requirements which were running in parallel, making sure that all the development groups, they can write down their requirements, let's say, somehow in parallel. And that was basically the management of these requirements, to have a systems engineering-based language, which allows you to automatically then process the requirements. It's not about the, let's say, the calculation at the end, because the result is basically the same. You have a requirements handbook, and that one, then you will implement in principle.
I suspect the question is different because Alain just wrote the same, I think it's the same thing. I think they're talking about processing power of co-simulation. At least let's try Alain's question. In co-simulation, FMI modules are used to interconnect tools, but FMI increases the computational time. Is it a problem for hill testing with real-time simulation? I suspect that is a question. It's about processing power, computational time, particularly when you're in co-simulation in your black boxes. Is it a problem for computational time?
Well, FMI definitely is a topic. I mean, we did exchange on that, as you saw. So that means there are lots of topics of discussion between the people. That's very clear. Of course, it depends really on the FMI-FMU model that you have. Maybe you have to update this again if it's computational too much demanding. And of course, let's say even the developments of HIFI-ELEMENTS will not, let's say, completely mitigate this problem just by saying we have the standard. You still have to work, of course, on the efficiency of the models, and then it comes basically to the question, when you want to do a real-time simulation again, you want to use low fidelity and high fidelity models. But the co-simulation tool can do quite a lot of things. Sometimes it really helps you also to do massive parallelization. I mean, it has some setup efforts, however, but then you could run it on a separate machine, have the co-simulation tool just, let's say, running this high resources demanding simulation model on a dedicated machine and do the rest on the other things, on the remaining hill. So this is in principle possible, of course.
So it's a win-win. Yes, it works, and yes, there's more work to be done, which is exciting.
Yeah, somehow. I mean, it's always a trade-off between different things, and but it gives you lots of opportunities. But sometimes, of course, some efforts will be there, and maybe modelers have to update things. Yeah. So we have the standards now. Let's say the architectural standards, and next step is just to make sure that also the functional requirements they really are satisfied. Mm-hmm.
Okay, Jens, thank you very much for your time and for your interesting overview. Thank you.